In this session, let us take a brief overview of the HBM4, that is high bandwidth memory 4. So as part of that, uh, we'll start off with understanding what all things we'll be covering as part of this course. Then we'll understand what is the sudden push that is happening for HBM4 across different design implementations, and then we'll try to understand how HBM4 differs from the traditional DDR and graphics DDR kind of memories. So first, let's start with understanding the what all aspects are covered as part of the HBM4 training. So initially, we would start with understanding some basics of memories in the SoCs. Like we would start with understanding what is DDR and what is the significance, and what is the storage memory, and how system memory differs from the storage memory. Uh, then we'll understand the HBM4, the features and the organization. I mean, how the HBM4 memory is organized in terms of high stack. See, as we go forward, we'll see that HBM4 is built onto the SoC through something called as the interposer and through silicon vias. That allows to keep the HBM4 memory onto the chip. Generally, the DDR is placed around the SoC on the motherboard, which increases the trace length of the connections between the processor and the memory. Whereas in HBM4, since the memory is kept onto the SoC, the connection length will be very small. It will be in millimeters, but it brings its own challenges. So we'll understand how that memory is organized. So because it is placed onto the SoC, it has to be a three-dimensional memory where dice are stacked vertically on top of each other. So we'll understand all those aspects of the memory organization. So we'll also understand the concept of channel, pseudo channel, and how the channel addressing is done. And we'll also discuss about the state diagram for the HBM4 memory. And we'll also talk about initialization. As part of the various aspects of initialization, we'll be talking the HBM4 power up and initialization sequence, the controlled power off sequence, the initialization sequence with stable power, and the initialization sequence for use of IEEE 1500 instruction, including lane repairs and channel disable. So we'll discuss various aspects of the HBM4 initialization. And then more importantly, we'll also talk about the mode registers. So HBM4 has around 16 mode registers. So we'll discuss about all the aspects of the mode registers. I mean, all the fields of the mode registers and the significance. We'll also talk about HBM4 clocking overview. So what are the different clocks? One is the clock that is used for driving the control and address information. The other one that is used for driving and sampling of the data bus. Then we'll also talk about the HBM4 data bus inversion, the commands, the row commands, the column commands. Then we'll talk about the parity feature, the clock frequency change sequence, the temperature compensated refresh reporting, then interconnect redundancy remapping. We'll also talk about, as part of that, we'll talk about D word remapping and A word remapping. Then we'll touch upon loopback test modes. Then A word and D word write register modes. Then D word read register mode, D word LFSR mode. Okay, so this all will be part of the loopback test modes. A word, D word, write LFSR compare modes. Then we'll talk about on-die DRAM ECC concept. Right, clock oscillator we'll talk about, and duty cycle adjuster and duty cycle monitor. We'll also talk about the self repair concept that is implemented in HBM4. You see what happens anytime there is a fault, there is a concept in HBM4, up to two connection faults can be repaired. So how that is implemented, we'll discuss. Then we'll also discuss about some basics of operating conditions and electrical characteristics. We'll also talk about IDD specifications, AC timings, and package specification. I mean, what is the placement of the bumps and micro bumps we'll talk about. Then we'll discuss about how the DRAM assembly works in HBM. And the most one last topic we'll discuss is about the test and boundary scan. And there we'll talk about direct access test port and IEEE standard 1500. So there are two ways that DRAM internal can be tested. So we'll discuss about both the test port and 15 IEEE standard 1500. As part of that, we'll talk about wrapper data register types. and test IEEE 1500 tap instruction encodings also we'll talk about. So this is a brief about what all agenda that will be covered. So whatever we discuss as part of this course will be quite detailed. I mean, we'll be discussing the commands. I mean, from a practical perspective. I mean, let's say we talk about channel addressing. We'll discuss about how the processor initiates the transaction and how it targets a specific channel. So once the transaction comes to the HBM4 controller, how does it convert it into the HBM related signals, and how it targets a specific stack, specific bank. So all those things will be discussed. Even when we go to HBM initialization power up, we'll discuss all the aspects. Okay. So same thing, pretty much every aspect of the training, we'll try to take a use case examples and try to understand through those things.
This conference will now be recorded.
Hello everyone. In this lecture, let's understand what is the need for high bandwidth memories. First of all, let us start with understanding what is this sudden push for high bandwidth memory uses across data centers and the server applications. I mean, one of the thing that comes to our mind whenever we say high bandwidth memory is the its uses in the artificial intelligence and machine learning. So the AI ML compute requires a good memory architecture. I mean, it is very memory intensive jobs, right? I mean, it requires a lot of data transfer between the memory. Memory is required. I mean, this memory is required to store and retrieve trillions of calculations. So let's try to briefly understand where is this calculations are coming into picture. There's a point at which adding more CPUs doesn't increase the system performance because the memory bandwidth isn't there to support those many number of CPUs. That is what we call as infamous memory wall bottleneck. Generally, the requirement is to have one 4 gigabytes per core, CPU core. So as you see, when we are reaching the bandwidths of 190, I mean 96 cores or 192 cores, so into 4 gigabytes when you do, so we end up reaching a limiting factor, right? And it also, because all these DDRs, the GDDRs or even the DDRs are connected at the periphery of the chip, that also becomes a limiting factor in terms of the bandwidth. Now, talking about AML, so they work on the basis of large language models. Okay, large language models use some billions of parameters. These parameters are fine-tuned by performing large number of iterations. Now, that iterations could be in terms of millions of iterations that need to be done till you achieve set of parameters that fine tune the, I mean, that are fine tuned for your require for the machine requirement till it achieves the best fit. These iterations could involve billions of bytes of data transfer. Now, what is that fine tuning these parameters has to do with the memory? It is because whenever we are doing fine tuning, we have to run that entire set of iteration, I mean entire set of operations all over again. So that involves large amount of data transfers between the CPU and the system memory. So HBM falls under a system memory category. It is not a storage memory. So the whole idea is to keep the system memory closest to the CPU so that you can reduce the length of the transfer. Let's say CPU and the system memory, as much as you can reduce this, as much possible we can reduce this length. So that will reduce the latency, that will also reduce the power consumption, right? Because you are having to traverse over lesser uh, distance. See, LLM limiting factor is moving data in and out of the memory is one of the limiting factors for LLM iterations. The giant set of memory values needs to be moved back and forth millions of times over a course of 2 months of training run. Let's say we are the LLM, the GPT model is being, I mean, trained over a 2 months period of time. So during that 2 months period of time, millions of iterations need to be done, which would involve large amount of data transfers between CPU and the memory, which are finally used for fine tuning some large number of parameters. What is large set of parameters? Some billions of parameters are fine tuned. Okay. So let's not deviate into what exactly is LLM, but understand that it is very data intensive requirements. So this is where there is a need for high bandwidth memories. So first of all, let's try to understand what is the limitation with the existing DDR or the graphic DDRs. So if you see, this diagram shows us what major limitation, I mean major difference between the DDR5 and the HBM. I mean, whether you say DDR5 or graphics DDR5, these are all the off-chip memories. So this off-chip memories is what we are calling as the DDR, and this one is the CPU or the GPU, and that is the silicon die basically, in which you have the CPU, GPU, and at the periphery of the chip, you are connecting the different DDRs. Okay, and this is the substrate. Okay, on substrate you have the silicon die, and that's connected. Whereas coming to HBM, the memory is fabricated onto the silicon itself, onto the substrate itself. So how it is done is, see, the black one you see is the package or the substrate. On that, we have something called as interposer. What is interposer is, it will have some kind of bumps. What is bumps is some kind of pointed things where you can plug in whatever circuit you want to plug in, and then they get soldered, right? I mean, they get connected essentially. And then you have one more connection where you are connecting something essentially internal to the interposer. Internally to the interposer, there is a connection established between these two, let's say here. So essentially these two dies are getting connected. Let's say it could be GPU, it could be HBM. So essentially there is a connection established between these two things by means of the interposer. So you see, this one is the CPU or the GPU. These are the stacked memories. This one is called as logic die. This one is the logic die. And basically all the HBMs are sitting on the logic die. The logic die is sitting on the interposer, and even the CPU, GPU is sitting on the interposer. Internal to the interposer, there is a connection going inside of the interposer, which is connecting this logic die to the CPU or GPU. So this is how you don't have to connect them off chip. They are connected on chip, and the distance is very closest. So that is where we get minimum latency and the better performance at a low power consumption. Okay. So let us now understand some of the limitations of the DDR or GDDR. So the rising power consumption limiting the growth of graphics performance. I mean, since these are kept at a far location, that results in a large amount of power drop, voltage drop, which essentially results in a increased power consumption, and also large form factor to address the bandwidth need for GPU and CPU. And multiple chips are needed to achieve the required high bandwidth with necessary power circuitry. It is not ideal for on-chip integration. Okay, these are some of the limitations of the DDR5. That is where the HBMs have evolved. So now, how does HBM look like? As I have shown you earlier, the substrate, package or substrate, on that you have an interposer which spreads throughout the connection where you have to keep the things. Going forward, we'll see that these are the few things that actually increases the cost of the HBM, and they become the drawbacks of the HBM. Okay. Now you can see that you have a on the interposer you have got multiple bumps. Okay, I mean, in physical design terminology, these are called as bumps. I mean, how you may say, what is the difference between other things? What you come as a outside is the IO ports. These are not technically called as IO ports. These are being called as the bumps. Okay, on the bumps, you are connecting CPU or GPU or whatever SoC die you have, and you have a logic die, which also has the phi circuitry, and to that you are connecting different this thing. So this you can think of as a one HBM cube. So also we see that going forward, we'll see that there is a limitation in terms of number of HBM cubes that you can connect, because there's a limited area here, right? Whereas coming to the boundary, you could still increase this thing and you could connect more number of memories, and also there is no limitation on how much you can keep, because you can keep many memories and increase the number of ranks, but having the limitation in terms of number of channels. You have less channels, but you have more ranks, so you can still increase the capacity of your DDR, But whereas HBM, you have a limitation in terms of how many connections you can do, so that limits the capacity of the HBM. So there are some advantages of HBM, there are some drawbacks. So let's focus on all of them in current session, in present session. So HBM offers a compact 2.5D form factor, enables significant reduction in the latency because these are closely connected. See, this is what is the closely connected thing, right? Because of that, the latency is very minimal, and also a very small footprint. I mean, in a small area you're able to uh, fit in large amount of things because of the 2.5D form factor stacking. I mean, you're stacking over one over each other, and they provide good power efficiency. Because of the reduced length, the voltage drop is smaller, and it essentially leads to improved power efficiency. Now, HBM achieves higher bandwidth than DDR4 and GDDR5 while using less power in a substantially smaller form factor. These are achieved by stacking up to 8 DRAM dies. Essentially, HBM is a DRAM only. At its fundamental storage level, it's a DRAM only. It's just that instead of connecting these DRAMs off the chip, we are stacking them onto the logic die, which is sitting on the interposer, and an optional base die, which can include buffer circuitry and the test logic. So this is what we are calling as the logic die. Okay. The stack is often connected to the memory controller on a GPU or CPU through a substrate such as silicon interposer. See, where is memory controller is present on the GPU, which is connected to the memory HBM through a substrate which is present in the silicon interposer. Memory die could also be stacked directly on the CPU or GPU. So it is also possible to stack the dice on CPU GPU itself. Within the stack, the dice are vertically interconnected through silicon vias, TSVs, and micro bumps. So if you go back here, so this is what we are calling as the TSVs. I mean, through the silicon, you are taking the connections like this. Now, how it is done at the fabrication level, I mean, we have to go and understand how the TSVs work, how do they ensure that there is no short happens. All that will be part of the fabrication. But what it ensures is that you are able to access whichever die is required, basically. So this large number of connections to different dies makes it a very wide interface. I mean, you are able to access large number of things because of the 3D stacking that you have done. I mean, multi-dimensional stacking you have done. So in one axis itself, as we go forward, we'll see that we are able to access 4096 bits of data can be accessed in one cycle. That is why it's a wide interface protocol. Next. Okay, which we have discussed. Then going here, HBM memory bus is very wide in comparison to other DRAM memories such as DDR4 or GDDR5. An HBM stack of 4 DRAM dice. So one we have seen just now. Okay, there are 4 DRAM dice, right? Uh, can has two 128-bit channels per die for total of 8 channels. So you can think of totally 8 channels. How does the 8 channels come into picture? So two channels here, two channels each of them, two channels, totally 8 channels. Okay. 128-bit channels, each channel is 128-bit, and 8 channels, totally 1000 bits uh, in total. So this is for one HBM device. Okay. Then a graphics card or CPU with the 4 high HBM stacks. What is 4 high HBM stacks? Is this one. This is this is called as 4 high. 8 high means 8 such will be there. 16 high means 16 high. Mean how much height you have, how many dice you have stacked together is the high factor here. So that essentially 4 HBM. See, one die can give us a bandwidth of 1024 bits. So four such stacks will give you up to 4096 bits. Would therefore have memory bus width of 4096 bits. In comparison, the bus width of GDDR memories is 32 bits. Only the bus width is 32 bits.
It supports up to 16 channels for a graphic card. So the 16 into 32 will translate into 512-bit memory interface. So that is where this is one of the factors that contributes to the high bandwidth in HBMs. We are able to take the advantage of that stacking, 3D stacking with with the TSVs, which are able to help us uh, push through 4096 bits of lines through all these stacked HBMs. HBM supports up to 8 gigabyte per package, and it could be higher, even it could be 8 gigabyte as we go to HBM3. Because as you know, with every generation of the memory, you try to increase the capacity per package. The larger number of connections to the memory relative to DDR4 required a new method of connecting HBM memory to the GPU, right? I mean, because you have large number of connections, you cannot spread the memory like this. You should rather do the 3D stacking. So that is what has been done. So the AMD, NVIDIA have both used purpose-built silicon chips called as interposers. So they have used, these companies have used something called as interposers to connect memory to the GPU. This interposer has an added advantage of requiring memory and processor to be physically close, because interposer cannot be too wide, so it is limited in size, because as you increase the size, it adds to the cost of the fabrication. So hence they need to limit that. Because of that, it adds an advantage, it becomes an advantage, because memories and processor automatically become physically closer, which decreases the memory path, and which essentially reduces the latency, which also essentially reduces the power consumption. But on a negative note, on a negative side, because they're placed close by, memory and processor are placed close by, the processor generates a lot of heat that has a negative impact on the memory performance. However, as silicon device fabrication is significantly more expensive than printed circuit board manufacturing, this adds cost to the final product. See, it is silicon interposers is nothing but a printed circuit board only. You can think of it like that. So you have got different a circuit board where you have various components connected, and they are being connected on the PCB. Now all that we are doing is this connection we are establishing at the fabrication level only, by having one more layer called as silicon interposer in between, which through the interposer we take through the connection. Now you may say, why can't we do on a circuit board itself? The whole point of manufacturing connection here could actually be a difficult job, and it may end up having multiple connections overlapping, so which cannot be done properly. Let's now talk about some of the advantages of the HBMs. See, HBM stands out in terms of the maximum bandwidth offered, because it's a wide interface. So, in terms of the latency, in terms of the bandwidth, it offers very high bandwidth. HBM3 with 4 gigabits per second transfer rate can provide 512 gigabytes per second bandwidth. Okay. HBM2 was offering 307 gigabytes per second, whereas the comparable one, DDR4 DIMMs, offer 85.2 gigabytes per second. So you can see the significant difference between the bandwidth of DDR4 and this one. Even if you assume DDR5 can give double, that is, let's say 170 gigabytes per second. So this still a significant bandwidth improvement, right? Energy per bit transfer is also less, because the memory and the processor are placed close by. The power consumption is also lower per bit transferred. I mean, in case of GDDR5, it takes 10.6 gigabytes per second of bandwidth per watt. I mean, with 1 watt, you can do this much amount of data transfer. Whereas in HBM, with per watt, we can do 35 gigabytes of second bandwidth. That much transfer can be done. So that's a significant 3 times advantage in terms of the power consumption, and even multiple folds of advantage in terms of the bandwidth. But it also has its own drawbacks. So one of the drawbacks is the expensive. These are expensive to manufacture, because HBM relies on expensive silicon interposers and through silicon vias. HBM fabrication is expensive. Because of this, it becomes expensive. One is because of the 3D stacking of the dice, the logic die that sits at the base of the stack of dice, that also need to be fabricated as part of the stacking, right? it increases the complexity and the cost of the fabrication. And then the silicon interpose also adds to the cost. It goes under everything, like it will be below HBMs, it will be below CPU and GPU. So that additionally adding that layer of silicon interposer and taking the connections through that interposer will add to the complexity and the cost. This cost aspect make it only suitable for server and data center application. I mean, normal for consumer applications, HBM won't be of um, much use because of the cost involved in manufacturing. But for servers and data center applications, it would fit in. Okay. Whereas talking about GDDR6, they don't offer as much performance as HBM3, but provide the cost advantage. Performance per unit cost on GDDR6 is better compared to HBM3. I mean, the only advantage GDDR6 has is the unit cost. Okay, but HBM3 is expensive, that is in terms of cost. But in terms of the power efficiency, in terms of the bandwidth efficiency, HBM3 stands out compared to DDR and GDDRs. One other drawback with the HBMs is the capacity. So as I told you earlier, since I mean when we are connecting this thing, you can connect as many number of GDDRs you want here outside, right? Whereas here you have a limitation in terms of number of HBMs that you can connect. And also you can connect as much memory as you want, because why you can connect is you can connect and you can divide them into ranks. You can make it quad rank, octa rank, for example. And you may still have one or two channels only. You can select which rank you want to access, so you still have the capacity advantage here. Whereas here the problem is you are only relying on the 3D stacking. Now there is a limitation on how much stacking you can do, 8 or 16 maximum that you can do. So, and you are also limited by the amount of area and the number of pins, all that essentially ends up limiting uh, the capacity, memory capacity here. HBM is not like a standard DDR interface. DDR interface allows multiple channels of DDR with multiple ranks. HBM is defined as cubes. Basically, whatever we see is called as a cube, which are rigid. One cube, which with 4 devices high, that's called as 4 high, or 8 devices stacked, it's called as 8 high, 12 devices or 16 high in case of HBM3. This cube has a defined number of channels, I mean, which you cannot change. Okay, means what? You have got that number, right? 1024 into 4, those, that is number is fixed. 16 data channels which are of 128 bit wide, so that is one combination. Okay. Other one is what? 32 data channels of 64 bit wide, called as pseudo channel. Summary. So in summary, there is a limitation of on number of data channels and the size of each data channel. So that limits how much amount of data, how much amount of capacity that you can keep on per HBM. Also, we can't add arbitrary number of cubes, so there is a limitation. See, there is a physical layer that is going through the silicon interposer, right? I mean that there is a pitch that will be there between one pin to other pin, and the length of that is limited to few millimeters. I mean, the whatever silicon interposer we are talking about, that limitation will be, it will have a limitation in terms of how much, what will be the size of silicon interposer. Now how many pins can we accommodate in silicon interposer, that also limits the capacity of the HBM. So limits the number of HBM dies that can fit around the SoC. A maximum 8 cubes can fit in extreme case. Okay, it will be many years before HBM capacity can rival the capacity of DDR. As of today, DDR has advantage in terms of the cost, in terms of capacity. HBM has advantage in terms of the bandwidth and in terms of the efficient power consumption, power utilization. Okay. The one more drawback with HBM3 is the HBM is the thermal challenges, because the memory is placed close by the CPU. The CPU is the one which generates maximum amount of heat. It starts impacting the DDR performance. That is essentially the HBM3 performance. See, HBMs are 2.5D structure, traps the heat. These are exacerbated by, I mean, what is 2.5D means? You are placing one on top of other, right? This is exacerbated by the placement near CPUs and the GPUs. HBMs are theoretical example of poor design. I mean, if you ask someone to do a poor designing of an SoC, the current placement of HBMs in the SoCs is the example of a poor design architecture. But then there is no alternative, right? Since I mean, everyone is driven by more than power consumption, everyone is driven by the performance. So HBM with their stack of heat sensitive DRAMs are placed near to the compute intensive heat sources, that is CPUs and GPUs. See, CPU, GPU transferring terabits of per second. This much amount of data they are transferring per second. Even if one bit of data translates into picojoules, so you convert multiply picojoules to terabits per second, it translates into a lot of huge amount of energy being heat being generated, which are placed near to the HBMs. The essentially the DRAM. As you know, DRAM performance degradation starts with 80 starts from 85 degrees centigrade. Its operation is not guaranteed after 125 degrees centigrade. Once you hit 125, you can not say anything about DRAM performance. But what is the saving grace in all this is a 2.5D stack provides physical separation between the CPU and the HBM. See, when you're doing 2.5D stacking, there is essentially some kind of physical separation is coming between the CPU and GPU, HBM. They are not physically connected to each other. Mostly companies try to find ways to cool or reduce the heat around the HBM. So they don't try to compromise on the performance. They rather find a ways to reduce the temperature or cool the area around the HBM. So this is a brief about what is the need for HBM3, the advantages of HBM over the DDR, traditional DDR, and what are the drawbacks with respect to DDR.